All right, in the previous video, we converted this force vector into its horizontal and vertical components, right? But do you really need to find this thing to actually find this force, which Sisyphus is using to move this boulder upward? Well, it turns out that you actually don't. Okay, you don't need all of that. You don't need the things. You can use a very simple, use less tapes, with minimal effort and find the force, which I will show in the next couple of videos. And yeah, so before finding the force, this force, let us try doing a simpler question. Okay, let us try doing a question in a normal surface. Okay, not an angle, not an inclined plane, a normal flat plane. Okay, so let me draw a flat plane right here. Okay, cool. And let us take an object. Okay, let us take a box. Okay, this is a box, nice square box, and let's stick up some numbers. Okay, let's make it have a mass, which I'll denote as m, to be 10 kg. All right, cool. 10 kg mass in a box. Yeah, and it is in rest. Okay, it is in rest, and that means it has no unbalanced forces. Okay, why? Because of Newton's laws of motion. Okay, if there is an unbalanced force, it will move. But if there is no such unbalanced force, that means there is no net force, it will not move, right? It will not change the state of its motion unless there is a unbalanced force. And that means there are some forces which are canceling each other out. So which are those forces? So the first force is the force of gravity, just like in the first case, in our Sisyphus case, which I will draw like this, and it is acting downward. All right, it is acting downward, and the plane itself is providing a normal reaction, which is balancing, which is making this block stay on this flat surface and not go deeper and deeper into the earth, right? So there is a normal reaction, which I will draw with a nice blue color, which you cannot see. So let me switch it. Just a second. All right, fine. Yes, this one. This seems fine. Okay, let me make it. Let me wipe this mass thing. Okay, let me wipe this down, and like I'll write it later here, and let us draw the normal reaction. Okay, cool. Okay, all right. That seems to be the same length. Sorry about that. Okay, so this is the normal force, normal reaction. Okay, let us write the mass right here. Mass. No, let me make it right here. 10 kg. All right. 10 kg. Okay, cool. So these are the forces and they are balancing each other out. Okay. So can we put this in the Newton's second law of motion, right? Which states that the force, the net force to be very precise, equals the mass of an object times the acceleration. And if we switch things around a bit, acceleration equals the net force. The net force times, not times, over the mass, right? And in our case, it is having an acceleration of 0 because it is not moving, it's in rest. So 0 equals the net force times the mass, right? And if you cross multiply this mass over to this side, it will just be 0. Okay, because you multiply with 0, it becomes 0, right? So the net force is 0. And what are the forces? Mind you, I'm only talking about the vertical axis here, okay? Because there is only forces in the vertical axis. So let me write that down because I don't want you to be confused, right? Okay, this is only about the vertical axis, okay? So in the vertical axis, what are the forces? Okay, we have a force of gravity, which is acting downwards, and by convention, I'm taking the downward as negative, okay, as negative. So we have a downward force of gravity, okay? And let me write a 0 up right here, okay? And we have a positive, that is upward force of normal force, that thing. So normal Okay. And if we shift the force of gravity to this side, right? Force of gravity to this side, it equals to the force of normal reaction. And I think I should make it clear that this is only the magnitude, okay? Only the magnitude, because the signs are different, right? The signs should be, different because they're acting in the other directions. So the magnitude of the force of gravity is equal to the magnitude of the force of normal force. Yeah, to the normal force. And that is why it is in rest. And that makes sense, right? That does make sense. So let me just copy these into a different layer because, it is getting messy. And now we can write things here, right? So what will we do now? Okay. So I'm going to try something else this time. Okay. Let me extend this a bit, okay? So, imagine there is a person that is pulling this block, okay? That is pulling this block with a rope or something like that, like this, okay? This is a rope and it has a tension, which is also a kind of force, which acts away from the object, okay? Acts away because it's pulling, right? And it has a, let's call it T1, okay? Tension force T1, okay? It is, let's say, let me draw a thing here, and it is at an angle of, say theta, okay? Let's make it a bit generalized, okay? Theta. And it is pulling, but it is not moving, okay? It is not moving, it's still in rest, okay? And you know what it means to be in rest, that it has no acceleration, right? Okay. So what we will try to do here is to see what forces are balancing each other out. Okay. Okay. Cool. In the last example, last thing that we discussed, the force of gravity equaled to the force, to the magnitude of the normal reaction. But in this case, it's a bit different, right? Okay. Cool. So we'll see what's going on in this scenario. Okay. Let us write the equation again, the Newton's second law of motion, but this time using that thing, that acceleration thing. Yeah. So the acceleration equals the net force over the mass. Now, before doing that, I should probably have solved this into its vertical and horizontal parts. So let us do that right here. Let me draw a couple of things. So this green vector right here, it represents the vertical component, and this blue vector right here represents the horizontal component. Okay, and we know from the last video that this will equal to the magnitude of our t1 vector times cos theta. Okay, and this will equal to the magnitude of t1 vector times sine theta. Okay, cool. So, cool. So there are no forces in this direction, and that makes no sense because it should be moving, yeah? And there should be a force that's balancing in this opposite direction. Okay, that's why FBDs are really important. Okay, so let us make a vector right here, because you cannot have unbalanced forces, because otherwise it will move, and we have like made this block hard to move. It's not moving, right? So let's say there's another person pulling with a rope with tension T2. Okay, cool. So we can see right here that T1 T1 sub x is balancing with T1 sub 2. Okay, so let us solve that for the x axis. Okay, for the x axis right here. Okay, we have no acceleration. And what are the forces right here? Okay, and by convention, this right side is positive, this left side is negative. So our T1 cos theta, that is T1 sub x, is in the positive direction. Let me write that here. And our T2 is in the negative direction. Okay. And we have our mass, that's 10 kg, right? So that's 10 kg. Sorry about that. We can also write as mass, because it's 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 gonna get multiplied with 0 anyway. Yeah. So in that case, we can multiply that. I'm gonna skip that step, and we're gonna just bring the t2 here, on this side, and it will become positive, right? Equals to t1 sub x, that is just t1 cos theta. So we just proved that these forces are balancing each other using the second law of motion, right? And let's do that with our y-axis, okay? So let us take it for the y-axis, okay? Let me write that down. Y. Okay, cool. So again, this time we have a 0 acceleration because it's in rest. And again, we have a couple of more vectors right here. We have the normal force that's in the positive. We have the t1 sub y that is also in the positive, okay? That is upward. Okay, so let's write that down. T1 sub y, the vertical component of T1, and our force, our normal force right here, both are in the positive. And we have a negative force that's acting downwards. That is the force of gravity. Okay, I'm gonna make that here. Okay, cool. And we have a mass of 10 kgs, which is going to get multiplied here. Okay, so we're gonna again skip that step, and we bring the force of gravity this side, and that will become force of gravity equals our t1 sub y, that is t1 sine theta, plus our normal force. Our normal force, yes. So why did I just do that? Okay, why did I just do that? So this is the basic, understanding to solve other kinds of questions, this kind of questions. Because what happened in the last case? What happened in the, that last case? Where was it? The thing, this one, right? In this case, when we had just the normal force and just the force of gravity, the magnitude of force of gravity was equal to the magnitude of the normal force, right? But in this case, in this new case, when we had a pulling force, and that too at an angle, okay, we could see that more forces are balancing each other out. Okay, we had this force, okay, let me write that with a different color, different visible color, I suppose. Yeah, this force, and this force in the x-axis. Okay, so that meant that this force, okay, our normal force and our t1 sine theta was being balanced by the force of gravity. Okay, and let me be very clear this time as well that these are only the magnitudes. Okay, only the magnitudes, because like their directions are different, right? So that's what happens in this kind of things. Okay, and that is how you can also find the force of Sisyphus in this case as well. Okay, and that's what we are going to do in the next video. Okay, so so what did we learn here? We learned how to find the forces that are balancing each other out to find the force that we need. Okay, so suppose you actually had something, let's say it had an angle of 30 degrees, and the T1 equaled, say, 50 newtons. So you could just put in those numbers. You could just put in the place of T1, you could just put in 50 Newton. In the place of cos theta, you could put in 30 degrees, and you could just calculate it, right? You could just make the calculation and do your stuff, because that's physics, right? You just put in stuff, you calculate that, and it's done.